Most of the experiments that we have done in the previous lectures were based on ray optics approximation. We had mentioned that light is waves, but if obstacles or openings are much larger than the wavelength, then you can use ray optics approximation. You can assume light travels in straight paths and all those things. Now, let us talk of the wave character. Light is a wave, and now we know from theory, from experiments, that it is an electromagnetic wave. That means what changes with time and space? Electric field and magnetic field. For free space propagation, the electric field, magnetic field and the direction of propagation, they are all perpendicular to each other. The wave is generally described in terms of electric field, because once you know the electric field, you can always calculate the associated magnetic field. And if you write an equation for that, electric field you can write as E equals some E naught in some direction, and then sine or cosine, and K dot R minus omega t. And what are all these things? This E naught is the amplitude of electric field, K is propagation vector, and the magnitude of this K is related to the wavelength, and the relation is this magnitude is 2 pi by lambda. R is the space point where this electric field is being talked about. Omega is the frequency or angular frequency related to time period, 2 pi by t, and in terms of frequency it is 2 pi times nu. So, these are the parameters. Now, the best part is when two waves add, if at the same point you have two waves at the same point at the same time, then the waves add, electric fields add, and electric field will have some amplitude, but the amplitudes will also be accompanied by these phase factor, this sine cosine factor, and this can take place, this can take values from -1 to +1, and therefore the two waves which are adding, they can produce a constructive interference, a destructive interference. The net intensity is not the sum of the intensities of the two waves, but it depends on what is the difference in this part which changes the value of this sign. So, the whole thing may become a destructive interference where the total intensity is 0 at certain point, or it can be double the amplitude when the intensity will be 4 times, and so on. Now, this wave effect can be very easily shown by a very simple experiment, and that is diffraction experiment. If you have an opening, say a rectangular opening in some opaque board. So, my board is perpendicular to this plane of the blackboard or green board, and then in this board we have some kind of an rectangular slit or opening, and now if I send light and light go through this, and on the other side if I collect at a large distance, if I collect the light, then at any point of the screen light reaches from different portions of the slit. And these different portions, these different wave parts which are reaching here, originating from different points of this slit or different portions of this slit, will have different phases, and when they add, they may give you a pattern of changing intensity which we call single slit diffraction pattern. And it so happens that if your screen is far away, if the incident light is parallel and all those things, the intensity which you receive here can be written as I equal to I naught sine square beta over beta square. Now, what are this I naught and beta? If you take the symmetrical point on the screen, the intensity here is I naught. This is a rectangular slit, and then right in front of the center you take a point on the screen, and there the intensity is this I naught, and beta is pi over lambda b sine theta. So, I have introduced two new parameters b and theta. And what is this b? B is the width of this slit, this width. This is known as b. Lambda is of course the wavelength. And what is this theta? If you are looking for the intensity at a certain point, and if you join this middle point of the slit to that point of observation, the angle made by that line with this symmetrical line is theta. So, if this distance is large and is say capital D, and this distance on the screen here is y, then you can say tan theta is y by d. So, with each point on the screen there is a theta. Theta equal to 0 means you are looking at the central point, and then different thetas mean different points on this screen. So, that is the equation. With that you can calculate the intensity in terms of this I naught. But if I show it graphically how the intensity varies, that graph turns out to be something like this. So, now I am drawing the graph, and this side is sine of theta, and if theta is small, if this y is small, this tan theta is also almost same as sine theta. So, we are plotting sine theta on this side, and this is, let us say, theta equal to 0. So, sine theta equal to 0, and then you have theta, positive theta on one side, negative theta on the other side, and it is something like this. Symmetrically on the other side. Something of that sort. What is this side? This side is intensity, and this is I naught. This is the central point, and this is the intensity is I naught here. This is sine theta equal to 0, and this point here is sine theta equal to lambda by b. This is intensity 0 here, and intensity 0 is when beta is pi. Beta is 0, then sine beta is 0, but then here also you have 0. So, this takes the form 0 by 0, and in limit this will be 1. So, it is I naught, I is equal to I naught when beta is 0, and beta is 0 when theta is 0. So, at here it is I naught, and then when beta is pi, sine of pi is 0. So, this is equal to pi, and therefore, sine theta is equal to lambda by b. On this side it is minus lambda by b, sine theta is minus b, then this is 2 lambda by b when sine theta, sine of 2 pi is 0, so beta is 2 pi, and so on, minus 2 lambda by b, and so on. So, what does it say? It says that right at the center the intensity is very high that one expects. You have an opening and then the light is going, and right at the center intensity is high, good, and then the intensity decreases and becomes 0 at certain places on this screen where this theta satisfies that sine theta is lambda by b. So, when this sine theta, which is almost tan theta, which is small y by capital D, when that is equal to lambda by b, then the intensity there will become 0. On the other side also, when this sine theta becomes lambda by b, on the other side intensity is 0. So, from that place to that place, you will have a bright band, maximum intensity at the center, intensity will decrease and become 0 somewhere here. And after that again it should increase according to this figure. Again the intensity increases and becomes a maximum. Of course, not that strong maximum, it is I naught here, this is almost I naught by 22 or so. So, this intensity is small as compared to the intensity here, nevertheless in its own neighborhood this is a maximum. So, you have a bright band, then you have dark, and then again you have a bright band which is not that bright, not very bright, but still in its own neighborhood it is a band, and then again intensity becomes 0 and again it increases. So, you have alternative dark, bright, dark, bright type of pattern. The central bright will have a width minimum to minimum is 2 lambda by b, but then the other brights will have a width of lambda by b only. So, this is how you should expect from a single slit if you pass light through single slit and collect it on the other side. So, let us do the experiment and see if we get this type of result. So, to make the slit, what we have done is we have taken two pieces of razor blade, and these two pieces are placed parallel to each other on this compact disc. And how it is staying here on this disc, these two blades or these two pieces. For that, look at this side, we have put two small magnets here on the other side. So, these magnets are holding the two plates, and we can adjust the separation manually and make this slit a very narrow one. So, between these two pieces of the blade you have an opening from which a light will be sent. And the light we will be sending is from this laser. This will give me green laser, monochromatic, nearly monochromatic, because as you had seen here, all these positions of minima and all these things, they depend on wavelength, and if you have a mixture of wavelengths, then the pattern will not be sharp. So, the diffraction experiment should be done with a monochromatic source of light, and this anyway gives very nearly parallel beam. So, we do not have to do anything for making the beam parallel. Okay. So, we will set these two things and then we will see how the light goes. So, light is passing through this opening and falling on the screen, and you can see that this is the central point and this is that central bright fringe, and then you have dark here, and then again bright, less bright, then again dark, and then again bright, and so on. You can count, there are many, 1, 2, 3, 4, 5, 6, there are many on one side and also on the other side. And as expected, the central one is wider and the other ones are less wide, and these other ones are of almost same size, and the central one is almost double of this. That also you can verify. The intensities, the width, everything is as we wrote on the board. We had shown you the shadow of a wire, if you remember, in one of the previous lectures. So, we put a wire and sent this laser beam, and then on the other side we collected it on a wall, and you had seen the pattern, and that pattern was almost the same, similar as you have seen here in a single slit. Now this is a very general principle, it's called Babinet's principle. Suppose you have an opening in an opaque board, and on the other side you have an obstacle of same shape, same geometrical shape, so that if you put that obstacle on this opening is just one single flat thing, the diffraction patterns of the two are same. Therefore, this wire is like an obstacle and this slit is like an opening, and their patterns are similar. Now let us look at one more beautiful demonstration of this wave aspect of light, and that is diffraction by a double slit. So if you have two slits, let us say you have one slit here and then another slit here, and then you send this light beam, parallel light beam, and on the other side at a large distance you collect it on a screen, and then you have this central point on the screen where the intensity will be maximum, and then you look at some point on the screen away from the central point, and this distance is say y, this whole distance is capital D. Light reaches this point from the first slit and also from the second slit. How much intensity comes from the first slit and second slit? That depends on this width of the slit and then the angles. So from here light is going, from here light is going and reaching there. So from this slit, how much light is reaching here? That will be governed by the diffraction pattern created by this slit. And similarly, from the other slit, how much light is reaching this point will be dependent on the diffraction pattern of this second slit. But these two wave components which reach there, they also have some phase difference, and they themselves interfere constructively or destructively or some kind of superposition depending on what is the phase difference between the two, and hence the intensity varies on this screen, and that variation is now governed by two parameters or two components. One is the width of the slit, this one, and then the separation of the slits, and it is given by I is equal to I naught sine square beta over beta square cos square gamma. I have already told you what is this I0, this is the intensity at the central point. Beta, I have already told you, beta is pi over lambda b sine theta, where b is the slit width, this is b, this is b, assuming both the slits are of the same width. So width of any of these two slits is b, and from there you construct this beta. Theta is the angle at which you are looking the intensity, and you have gamma here, which is pi by lambda d sine theta. So another new variable comes in, d, and that d is center to center separation between the two slits. So this is d, from this center to this center, this is d. And how does this look like? If I look at the intensity, how does this formula or this equation, what does it tell? What kind of intensity variation is there? And that intensity variation, once again, if you make a plot, and here you write sine theta, and here you write intensity, it is, first you draw the diffraction pattern, this diffraction pattern, and you know what kind of pattern it is. it is something like this. And then, and this is governed by, this is what? This is lambda by b, this is minus lambda by b, and so on. This is 2 lambda by b, and so on. And then because of this factor cos square gamma, because of the presence of these two slits, two similar slits, you have in fact intensity goes like this, something of this sort. So this is the actual intensity. The diffraction one was just an overlap, was just an envelope. Like this. So the intensity variation is given by this inner line. If you wish, you can remove that outer envelope, and this gives you the intensity. Graph of intensity as a function of sin theta, like this. This is the kind of intensity variation. So you have a central fringe here, quite bright, and then you have adjacent fringes here, somewhat less bright, but important thing is width of the central fringe is same as the width of this adjacent fringe, and in fact all the fringes, but the intensity goes down, 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 governed by the diffraction envelope, and then once again here the intensity increases, but you have several maxima inside. So within that diffraction envelope you have these interference pattern. It is not very difficult to arrange for a double slit. Remember, all these widths should be small, so that we can, it should not be very large as compared to the wavelength. So you should not take in millimeters, make it as small as possible, 10, 15, 20 micrometer will be good. To make the double slit, we have taken once again a CD, and across that central hole we have fixed a thin wire, and then you have two pieces of this razor blade, and these two pieces of razor blade we are putting on the two sides of this wire, and of course they are staying here because of the two ring magnets on the opposite side, and we can adjust the position so that the wire is between the two edges and the two edges are equidistant from the wire, and the distance is quite small as possible. So we can adjust that edges that way. So you can see the pattern. You have at the center you can see three very bright fringes, and these are of equal width, that is important. For a single slit, the central one is much wider than the others. Here the central ones are also equal width, and then you have a variation in intensity, and you can see some bright spots, and between two brights you can see a feeble maximum on the two sides of the central bright thing. If you go to the left or you go to the right, you can see some bright fringes, bright spots, and in between two consecutive brights you can see some less bright fringes. So, that is the kind of double slit diffraction that you can see, and that is consistent with the formula that we have written on the board.